condition we are going to learning the about the how the ultimate bearing capacity it will may get vary when water table is lying directly below the base of the footing or base of the foundation. This is your footing. If suppose water table is directly available here, in that situation the soil what is available here, how it will may get affected. Otherwise if water table is presenting in this base above the base of the foundation, the water table is at this height, and how the bearing capacity, the load carrying capacity of the soil available here, it will may get where that we will discuss. Next, if the water table is at the ground surface, and this is your ground surface, if water present here, and how the load carrying capacity of the soil when the water table at base of the foundation, that we will see in this next session. Okay, and next if you observe here, if you observe in this diagram, shallow foundation bearing capacity, when water table is located above the base of the footing, when water table is located above the base of the footing. If you see here I am considered the one footing, and if you see here I am considered the one footing, and this depth of the footing I am having here as depth of the footing, I am taking it as df, and this is the width of the footing. That width of the footing we are taking it as b. And again if you observe in this diagram, by seeing diagram itself, we are having depth of foundation df by b is less than or equal to 1. That means depth of foundation is less than or equal to b. That means width of the footing is more compared to the depth. Hence why Tejagi's bearing capacity equation is satisfied. That means here the assumption is satisfied. And again if you see here, this is the water table above the base of the foundation or above the base of the footing. This is your footing, and water table is having at a depth of dw. Water table is having at a depth of dw. In that situation, the soil above the water table, the soil what is available here above the water table, the soil may be bulk unit weight of the soil mass or a dry unit weight of the soil mass. If the water table is available here, the soil is either may be bulk unit weight or dry unit weight. Again, if the due to presence of this water table, the soil below the water table, it may be saturated condition or it may be in a submerged condition. We are considering this below the water table of the soil mass, we are considering it as a submerged condition, and above the soil, above the water table, we are taking it as a bulk unit weight of the soil mass as a gamma. In that situation, how the bearing capacity it will may get changed, that we will calculate. Okay, and again if you see here, the effect of surcharge is reduced as the effective weight below the water table as equal to the submerged unit weight. Due to the presence of water, already we know the bulk unit weight, dry unit weight, saturated unit weight, submerged unit weight. If suppose the soil is having some water content, the bulk density will make it different. If the soil having no water content, the bulk density will make it different, and the soil is submerged in water. In that situation, the density will make it different. Hence why for this condition what we are calculating means, first we are calculating the surcharge pressure of the soil mass. The surcharge pressure already we have explained. The surcharge pressure we are taking it as Q equal to gamma into D into depth. Surcharge pressure Q equal to gamma into dF, where dF is the depth of the foundation and gamma is the unit weight of the soil mass throughout the depth of the foundation. If you observe in our present condition, we are having above here one type of soil, and below above the water table one type of soil, below the water table one type of soil. Hence why the unit weight of the soil mass for this depth of foundation will make it change. That is nothing but Q equal to surcharge pressure Q equal to depth of water table into unit weight of the soil mass. That is nothing but Q equal to depth of water table dW into unit weight of the soil mass gamma plus next we are having this depth what we are having, this depth we are having at x depth. From depth of the water table we are having the unit weight of the soil mass as gamma. Next they are given in the problem, they are mentioned in this diagram the depth of the water table below the base of the foundation, we are having x. That is nothing but x into this x, how much unit weight of the soil mass it is having. That unit weight of the soil mass x we are having, that is nothing but x into gamma sub, x into gamma sub. Again from this I am calculating q equal to depth of water table dw into gamma plus, and again now I want to calculate this x value. How x value we are getting? The x value we may get by division, by subtracting the depth of foundation if you deduct the depth of water table. This total depth of foundation I know, depth of water table I am reducing, then I will get this depth of the water table, how much depth it is having. That is nothing but x equal to, okay, otherwise what we can get? We can get depth of foundation df equal to dw plus x. Depth of foundation df equal to depth of foundation df equal to dw plus x. From this I will calculate the x value. That x value is nothing but df minus dw. X value I am having as df minus dw. That value I will substitute here. Here x value I am substitute this value as df minus dw. df minus dw into next we are having this gamma submerged unit weight. That is nothing but gamma submerged unit weight. Again if you substitute here we are having the depth of water table gamma. Here also we are having depth of water table gamma submerged. Directly from this we can write dw. If you take common, we may get gamma minus gamma sub into dw, as well as next we are having df into gamma submerged. These are the terms he explained here. That is nothing but q equal to gamma df. That gamma df equal to depth of water table into unit weight of the soil mass. Here this is the depth of water table. From this depth of water table having unit weight of the soil mass as a gamma. Next x into this much distance, x into submerged unit weight. Here this is the submerged unit weight of the soil mass. In this x, if you substitute the df minus dw, if you substitute the depth of the foundation and if you deduct this dw value, you will get this x value. That x value only he substituted, and directly he kept in formula and he substituted the surcharge pressure. Only because of presence of water table, the only thing is surcharge pressure, it will make it vary. Finally we are getting this value as gamma submerged into df plus gamma minus gamma submerged into dw. This is the surcharge pressure varying. Okay, next if you see here, where the ultimate bearing capacity Qu equal to Cnc plus, next we are having Qnq, where Nq is the bearing capacity factor, and this Q value submerged pressure we are having gamma sub into df plus gamma minus gamma sub into dw into nq plus 0.5 into gamma submerged. The unit weight of the soil mass we are considered for the below the base of the foundation. That below the base of the foundation, what is the soil we are having here? It is in a submerged condition. Hence why 0.5 into gamma submerged into B into N gamma. Again where NC, NQ and N gamma are the bearing capacity factors. The bearing capacity factors will be depend upon the angle of interflexion for the soil mass. Okay. Next we are having the one more term, that is nothing but when depth of water table equal to 0. When depth of water table is equal to 0, what we have to do? Just to substitute where depth of water table is there in the above equation, substitute the 0 value, you will get the one more equation. That is the equation nothing but Qu equal to Cnc plus gamma sub into Nc. Okay, gamma sub into Nc plus 0.5 into gamma sub into B N gamma. That means depth of water table equal to 0 means, okay, if you observe here, this x value we are having, that x equal to df minus dw. Instead of where dw equal to 0, we are having x value. That x value is df. That in that situation, we will substitute the x value to get the depth of water table. When depth of water table equal to 0, we are having CNC plus gamma submerged. Depth of water table equal to 0, hence we won't get this gamma submerged. Gamma NC value will get 0.5 into, that means depth of water table is at the below the base of the foundation, and below the base of the foundation the unit weight we are taking it as gamma sub into 0. Gamma sub into b n gamma. Okay, next when x equal to 0, that means depth of foundation he didn't consider in that condition, or the depth of water table is at base of the foundation. In that situation, QU equal to CNC plus gamma df into NQ plus 0.5 into gamma sub into b n gamma. That means suppose this is your type of the foundation and the water table is directly resting below the base of the foundation, and the water table is resting directly below the base of the foundation. The depth of the water table, that means the unit weight of the soil mass we are taking it as gamma submerged, and the gamma submerged value we are taking it as in a bottom of the foundation or bottom of the footing. That is the condition. Okay, these are the different types of conditions how water table is get affecting for the foundation. When the water table is at the middle of the foundation, when water table is at the base of the foundation, without water table is nothing but QU equal to CNC plus QNQ plus half gamma b n gamma. Suppose if the water table is having at the middle depth of the foundation, then CNC plus gamma sub df minus plus gamma sub into dw nq plus half gamma sub b n gamma. Suppose when depth of water table is 0 means it is varying. In that varying condition, this is the calculation for the ultimate bearing capacity. When depth of water table is at base of the foundation, then we have to use this formula for calculation of the ultimate bearing capacity. Based on this, again we will calculate the net ultimate bearing capacity, net safe bearing capacity, gross safe bearing capacity, net allowable bearing pressure. This is the discussion. Next, we are having one more term, that is when depth of water table is below the base of the foundation. That we will see in one next class. And next we are having the one more analysis for the calculation of the Terzaghi's bearing capacity theory. We have derived the bearing capacity equation for according to Terzaghi for general strip footing. Next, we are having different types of others. The others also, the scientists also, they also give the calculation of ultimate bearing capacity. Hansen's ultimate bearing capacity we are having, IS code method we are having, Prandtl we are having, Homo Gentler we are having. Different types of scientists also give the ultimate bearing capacity. But for our present syllabus, we are having Terzaghi's bearing capacity equation and as well as IS code method for calculation of ultimate bearing capacity. Next, here one more calculation for the bearing capacity equation, that is nothing but Hansen's bearing capacity equation. Hansen's bearing capacity equation. Hansen's bearing capacity equation is given as given formula, that is nothing but QU equal to CNC into SC into DC into IC plus QNQ into SQ into DQ into IQ plus half into gamma into B into N gamma. What is the equation you are having in Terzaghi equation? The same equation also we are considering for the Hansen's bearing capacity equation. The only difference is he introduced some shape factors. He introduced some factors for the calculation of the ultimate bearing capacity. Again, if you observe here, he introduced the SC, DC, IC. Okay. Next, he introduced the SQ, DQ, IQ. Next, he introduced the S gamma, D gamma, I gamma. These are the different types of factors invented by the given by the Hansen based on this shape factor, depth factor, and inclination factor. In terms of cohesion, in terms of unit weight, in terms of surcharge pressure, the ultimate bearing capacity value it will may get vary. Where this SC, DC, and IC are the shape factors, and SQ, DQ, IQ are the shape factors, and S gamma, I gamma and D gamma are the shape factors. While asking in our examination, calculate the Hansen bearing capacity equation, they will give the shape factors and they will ask to calculate the ultimate bearing capacity. And again, if you see here, where NC, NQ and N gamma are the bearing capacity factors. These bearing capacity factors already we have seen for the Terzaghi's bearing capacity theory. For general shear failure, how it will be. For local shear failure, how it will be. The bearing capacity equations we have seen. This SC, DC, IC, these shape factors they will given in our examination. If they are going, suppose they are going to ask by calculation of the Hansen's bearing capacity equation. And again, if you see here, where NC, NQ and N gamma are the Hansen's bearing capacity factors, which are somewhat smaller than the Terzaghi's bearing capacity factors. Okay, which are somewhat smaller than the Terzaghi's bearing capacity equation. For general shear failures, for angle of interpolation phi equal to 0, we are having taken the NC value as 5.7. The same factors also he are introduced to the Hansen. But Hansen take the smaller values compared to the Terzaghi, and he introduced to the some factors. And if you see here, where SC, SQ, S gamma are the shape factors which are independent of angle of shearing resistance. SC, SQ and S gamma are the shape factors. The shape factors will not depend upon the angle of intersection of the soil. If you take any angle of intersection of the soil mass, the shape factors it will won't vary. And where DC, DQ and D gamma are the depth factors. That means how much depth of the footing you are keeping and how much width of the footing you are keeping based on the depth factor ratio. These values will may get change. Next, IC, IQ, I gamma are the inclination factors. The inclination factors are nothing but, suppose if you are constructing the footing or foundation in any inclined direction, in that situation these factors will may get vary, and by using the Hansen's bearing capacity equation we can calculate the ultimate bearing capacity. Okay, for the ultimate bearing capacity according to Hansen's, we are having QU equal to CNC into SC, DC, IC plus QNQ plus SQ, DQ, IQ plus half gamma B, N gamma, S gamma, D gamma, I gamma. Okay, these are the different types of conditions for factors for the calculation of ultimate bearing capacity. Next, we are having the IS code method. In IS code method also, now we are taking this value based on the Hansen's bearing capacity equation. The only small difference they are adapted in the IS code method, but the shape factor, depth factor, inclination factor will make it vary compared to Hansenberg and compared to IS code method. While solving some examples of these problems, I will show the various type of shape factor, depth factor, inclination factor values. Okay, and if you see here, next we are having the same form of equation has been adapted by IS 6403 1917-1. IS 6403. This is the code, most important code for calculation of ultimate bearing capacity by using the IS code method. That is nothing but IS 6403. May be used for the general form as the net ultimate bearing capacity. Here they given the directly the net ultimate bearing capacity. The net ultimate bearing capacity QNU is nothing but we are having ultimate bearing capacity QU minus gamma DF. Otherwise, this also you can write as QNU equal to QU minus Q, where QU equal to CNC plus QNQ plus half gamma B N gamma. Q is gamma DF. Okay. From this, the net ultimate bearing capacity according to IS code method, we are having the formula that is nothing but CNC into SC into DC into IC plus QNQ minus 1 into SQ into DQ into IQ plus 0.5 into gamma B N gamma into S gamma D gamma I gamma. In some conditions, suppose if the water table is available, in that situation water table effect also we are taken. That means at how much depth the water table is available, based on that we will calculate the ultimate bearing capacity. Again here where NC, NQ and N gamma are the bearing capacity factors, where NC, NQ and N gamma are the bearing capacity factors. And again SC, okay, again SC, SQ and S gamma are the shape factors. S gamma are the shape factors. Again DC, DQ and D gamma are the depth factors. D gamma are the depth factors, and IC, IQ and I gamma are the inclination factor. The shape factors, inclination factors and depth factors, they will give in based on chart. In the chart value based on that given formula, we should have to substitute the depth of the foundation, width of the foundation. If suppose it is rectangular, again the shape factor it will may get vary. If it is strip footing, the shape factor it will may get vary. If it is square footing, the shape factor it will may get vary. Based on the type of the footing, we should have to use these shape factors and bearing capacity factors. We can calculate the net ultimate bearing capacity. Remember this formula: Qnu equal to CNC SC DC IC plus QNQ minus 1 into SQ DQ IQ plus half into gamma B and gamma into S gamma D gamma I gamma. If suppose water table is there, then you should have to substitute with the water table depth. If there is no water table, you need not to substitute this water table value. This is the calculation for that means calculation of the ultimate bearing capacity of the soil in a IS code method, or in IS code method, how the ultimate bearing capacity of the soil mass we are calculating. Next we are having the bearing capacity for clayey soils. Already we have seen this bearing capacity for clayey soils. Again I will write the formula here. That is nothing but the ultimate bearing capacity. We are having the formula QU equal to CNC plus QNQ plus half into gamma into B into N gamma, where NC, NQ and N gamma are the bearing capacity factors. Already we have know. Based on the angle of intersection of the soil mass, these parameters we are taking directly from the chart or directly from the table. And C is the cohesion of the soil mass, Q is the surcharge pressure, gamma is the unit weight of the soil mass, B is the width or base of the foundation of the footing or foundation. And again if you see here, bearing capacity for pure clayey soil, phi equal to angle of intersection phi equal to 0. When angle of intersection phi equal to 0, the bearing capacity factors, the Terzaghi's bearing capacity factor already I have explained. That is nothing but NC equal to 5.7 and NQ equal to 1.0 and N gamma equal to 0. These values must and should have to remember. Why? Because they will ask in your examination calculate the ultimate bearing capacity of the soil in cohesive soil without giving these parameters. Okay, and so you should have to remember these values for pure cohesive soils. And again if you see here, from this the ultimate bearing capacity Q equal to C we don't know. NC value we are having 5.7 into C plus Q is the surcharge pressure, that is nothing but Q or gamma DF. I am writing here gamma DF, and NQ value we are having 1.0, that is 1.0, and half gamma B N gamma value we are having 0, then it may get reduced to 0. Directly we are having the depth of the foundation, the ultimate bearing capacity for pure clayey soil, Q ultimate equal to CNC plus gamma DF, where NC is the bearing capacity factor phi equal to 0, 5.7 into C plus gamma DF. Okay, next Q ultimate bearing capacity. Q net ultimate bearing capacity. What is meant by Q net ultimate bearing capacity? That Q net ultimate bearing capacity is nothing but we are having the formula QU minus gamma into DF. QU minus gamma into DF. QU we are having 5.7 into C plus gamma DF minus gamma DF. Gamma DF will both may get cancelled. And the net ultimate bearing capacity for continuous footing in clays. For continuous footing in clays, we are having the formula 5.7 C. We are having the formula 5.7. Again, when depth of the foundation increasing, the ultimate bearing capacity it will may get vary. Again, when depth of foundation is at ground surface. Okay, if you want to calculate the ultimate bearing capacity at the ground surface, in that situation also the bearing capacity value it will may get a change. Okay, these are the different types of equations. And next, if you see here, the net ultimate bearing capacity for a square or circular footing, C being the cohesion. For square or circle, what we are substituting instead of strip footing, we are multiplying with 1.3. Suppose if you want to calculate the net ultimate bearing capacity for for square footing, here just we are substituting with 1.3. 1.3 into 5.7 into C. That means we are getting the square or circular footing, the net ultimate bearing capacity in Koju soil as 7.4 into C. This type of bits they won't ask in our examination of descriptive. There are chances for asking this type of problems, this type of questions in our objective type questions. Okay, they will give the dimensions of the footing and they will give the everything parameters. Just they will ask the calculate the net ultimate bearing capacity in a pure Koju soil. In that situation, directly should have to use the formula 7.4 into C. 7.4 into the cohesion of the soil below the base of the foundation. If you substitute, you will get the ultimate bearing capacity of the soil. Again, we need not to substitute to NC value, NQ value, and gamma value, as well as bearing capacity factors. Okay, unit weight to width of the foundation you not to submit. If you remember this formula, directly you can use this formula and you can get the ultimate bearing capacity of the soil in a square or circular footing based on the given dimensions. Okay, next we are having the modes of shear failure of the soil mass. Already this topic will explain the footing I have explained. If you observe in our general Dajagis bearing capacity equation, this is the type of footing we have considered here. Sorry, okay, no problem.